got to that point in the restoration where I actually needed to have a look at a few component values. So I've gone ahead and I've downloaded the operator's manual for this, and you can see that we've got the circuit diagram laid out here, and I thought we could just go over some of the work we've done. So the 230 volt input comes in here, and we talked about the fact that both of the live and neutral lines, they were both fused, and that's because the connector plug, it was a 2-pin plug and it was unpolarized, so you could plug it in either way around. So depending on which way you actually plugged it in, you wouldn't know which was the live or which was the neutral, so they actually chose to fuse both sides of the circuit, so that was good. And then we came to the two capacitors, which were the radio frequency interference capacitors, and again, as you can see, these are pretty much, I'm not going to say they're across the mains because these are actually a Y configuration. So we went and replaced these, and we replaced them with a capacitor that had X2 and Y rating. Sorry, it was X1Y rating. So those capacitors are safety capacitors suitable for being wired across the mains. We've got the on switch there. Here's the voltage selector. We've already checked that that's been set to about 240 volts. So rather than being at, I think, is that 200? It's actually set to the 244 volt input. There's our mains transformer, and then we had the high tension windings for the B plus voltage, as you Americans call it. And here's our full wave rectifier, and we did comment that when you have one of these full wave rectifiers with the two diodes, it's a center tapped configuration, and it is important that you take voltage measurements on each side of the center tap, and we went ahead and we did that. And here's a second winding on our transformer, which is the low tension, which supplies the power to the dial lamp. So when you switch the power on, you get a lamp coming on, a power on indicator, and this also supplies the heater current to all of the valve filaments. So we had a look at that and took a measure of that. I think that was about 6.5 volts, wasn't it? We also then went and talked about the main smoothing capacitors and the fact that the smoothing capacitors were using LC smoothing. So here's the first smoothing capacitor, here's the second smoothing capacitor, and both those capacitors were installed in the same can. So we've gone ahead and replaced them, but they're actually wired in series here with this inductor. So that's doing some smoothing. Now, interestingly enough, here we have a multi-vibrator circuit, and if you look at these two anodes, what we've actually got here, they don't actually show the valve envelope, but what we've got here, we've got a double triode valve. If you actually look at that circuit and think back to when we all used to build transistor, I think they were multi-vibrators, weren't they? Was it astable or bistable? I forget now, might have been astable, I forget completely. But we used to build these multi-vibrators with two transistors. Well, nothing much has changed in 70 years, or this circuit has a lot of symmetry with its more modern transistor equivalent. So I think this circuit is actually being used to chop up part of our modulated signal, and I think this is probably what's going to be responsible for generating the lines, if you like, on the screen of the pattern generator of the television. So I think that's what that's going to do. It's going to chop up the frame pulse to actually produce lines on the television screen, or it's going to affect the modulation of it anyway. One of the things that we need to do, we changed the main smoothing capacitors. We've also got coupling capacitors, and I actually mentioned, I think, that these are Hunt's capacitors, and these really get quite an unfair reputation because after 70 years or so you can't expect them to be perfect. But we've got 1, 2, 3, 4 capacitors here which have the potential to put DC on the grid of a valve, so really we need to take a close look at them. And I've already gone ahead and I've actually measured these, and well, I haven't done a leakage test, which is the most important thing, but I have actually measured the capacitance value, and it does look about right. So I think just for now, and I may live to regret it, I'm going to give these 3 coupling capacitors the benefit of the doubt. And what we might do is I'm going to put some power onto the equipment, and I will check the voltage on the grid of each of these valves. And if we see anything that's worrying, what we'll go ahead is we'll stop right away and we'll go ahead and address that. One thing that I did actually find though is that this capacitor here, which is an output coupling capacitor, which is actually feeding the attenuator stage, this capacitor, this 1000 picofarad here, this is measuring as low resistance. So this is a capacitor that I am going to go ahead and change, because the last thing I want is the B plus, the high voltage, to appear on the output of this pattern generator, because that could damage something that we plug into it. So we're going to go ahead, we're going to replace this 1000 picofarad coupling capacitor, and then I'm going to put the rest of the valves back in, plug it in, power it up and see if she chooches. So let's go ahead and do that. This is actually our C17, which is actually feeding the output attenuator from our final stage amplifier valve, and this one is actually measuring a bit flaky. It seems to be measuring all over the shop as being open circuit, closed circuit, and then sometimes it comes up as a capacitor. Now it could be that it's doing that because it's under some form of load, but kind of tapping it, touching it had an effect on it, so I don't think it is that. I think it's maybe just a bad capacitor. So that's what I'm going to do now. I'm going to go ahead and I'm going to swap that out, and hopefully then we can power it up. Okay, so now I've actually cut it out of circuit. It's actually reading as 2 picofarads, but oh, okay, so it's varying between, it's just gone up to now nearly 1,000 picofarads, but when I just plugged it in it said 2 picofarads, so there's something not right with it. Yeah, it's measuring 745 now, but when I plugged it in, yeah, it did definitely come up as 2 picofarads. So there's something not right with this capacitor, so that's going to go. And it's actually going to get replaced with another 1,000 picofarad capacitor. I thought that we really want to have very good isolation between any high voltages and any test equipment. And this, again, this capacitor is actually rated, I think it might be 400 volt nominal, but it's got a peak rating of 1,000 volts. So I thought this might be a good choice to put in place of that dodgy one. So let me go ahead and try and just solder that in. Now the other thing that's probably not a bad idea to do is actually to go ahead and spot check some of these resistor values. Probably should do that, but you know what, I'm not going to. Let's plug it in and see if it smokes. Now although they're all different sizes and shapes, I actually think all the valves in this are actually classed as being double triodes, which is, I guess, kind of interesting. And these valves here, these 3 little valves I'm putting them in, again they're all the same valve, same type of valve anyway. Now it's going to be interesting when we power this up to see if it actually works, or if I, very quickly come to regret not replacing those nasty Hunt's mole seals. As I say, they do get a really bad press, those capacitors, and I think it's slightly undeserved. But even back in the day, they weren't known to be particularly reliable, and I think the main reason that they got such a bad press is that the failure mode was that it used to often just split in half, and you'll actually quite often find them when you start playing around in a valve radio, that you'll just touch one of them and the capacitor will break in half, because what happens is the material, the plastic material, it seems to absorb water, and when it does that it seems to, I don't know if it swells on the inside, but certainly the outer packaging cracks, and it'll crack and the capacitor will literally just break in half when you touch it. So, that's a very obvious failure mode, and obviously a capacitor that falls in half is obviously considered worse than a capacitor that just stops working. So I don't know whether the reputation is totally deserved or not. I'm going to give any capacitor the benefit of the doubt that's lasted 70 years. I mean, at the end of the day, they never thought this equipment was going to last for 70 years, did they? So let's not beat these old manufacturers up too much. So I've just gone ahead and I've got our old friend, the Philips PM3217 oscilloscope out, and this is probably going to be really at the top of its range, because I suspect that the output from this signal generator should be around 50 megahertz, so we're going to be pushing it slightly because the bandwidth for this scope is 50 megahertz, but I'm sure it will work. And the main reason that I picked it is because at the end of the day, if we blow it up, I really don't care. And I've clipped the scope onto the input of the output attenuator, if you can follow that, and that's the capacitor that we just replaced a moment ago. So I think we're about ready to power this up, and I'm really not sure if it's going to do anything. Maybe the smoke will come out. I guess we'll just have to find out. So there's not a lot happening so far. I can't see any wibbly wobbly action. Oh, is that video? Is that video? is that noise? What we triggered on? Let me just see. Is that video? Oh, it might be video. So we have got something going on. Now this is where I'm going to show you how stupid I am. I can't remember how to drive an analog scope anymore. We should have something like a line time base on here. That's probably what I'm looking for, isn't it? Does it have a line time base? Not doing very well. We maybe sometime. I'm tempted just to leave your camera on and then you can just see what a complete moron I am. So what we're triggering on, AC, I think we only need one waveform. Let's put it on A.
Yes.
Oh, that doesn't help. There's definitely something happening there. Does this scope have a ×10 setting? Can we turn the frequency down? Well, this isn't great entertainment for you, isn't it? Watching me being able not to work a scope. Pull for ×10. Oh yeah, it does. So this has line and frame triggering. If in doubt, just twiddle buttons randomly. Right. Got somewhere. A. Well, it just so happens that an infinite number of monkeys given typewriters will eventually produce the works of Shakespeare. Well, if you give an electronics engineer, even an idiot like me, enough buttons to press and an oscilloscope, he will eventually manage to figure out how to trigger on the line sync of a television video signal. So, yeah, several hours later we have something on the screen. So I think this signal generator is working, but I think I'm somewhat struggling with my limited intelligence and understanding of both analog scopes and this pattern generator, but I certainly think it's doing something, and really I'd like to have a television to plug it into to test it further, and unfortunately that's something we just don't have at the moment. Well, I'm not exactly sure why, but we've actually got frequency control here and it says 70 megahertz, and I'm setting it to 70 megahertz, but according to the scope the output frequency is 128 megahertz on the carrier, so there's something not quite right. Ooh, oh, that shenanigan alarm's going off again. Well, I'm sorry about that everybody, but you know what it's like when you're working on a piece of vintage equipment and the shenanigan detector keeps going off. But I've gone ahead and I've just taken the batteries out, so I think we should be okay for now. What I think set our shenanigan detector off in the first place was the carrier tuning control on the pattern generator, and you can see here that it actually goes between 7 and 70 megahertz, so 7 at this end and 70 megahertz at the other. And if we actually have a look at the video waveform on the oscilloscope, I actually see something quite different to that, so let's take a look. So here's another of those video signals like we looked at last time, and what we can do is we can actually zoom into this. And you can see here's our actual carrier waveform here. But the problem I have is that I've actually set the carrier waveform on the pattern generator to about 70 megahertz. But for some reason, it's actually the oscilloscope's telling me we've got a carrier wave of 186 megahertz. So I think that's probably what set off the shenanigan detector, because there's something not right there. So according to our circuit diagram here, we've actually got an oscillator, and I was looking at this oscillator and it says it's between 122 and 185 megahertz, and it's got a variable capacitor here, and that's the frequency control that I was adjusting on the front of the instrument. But the actual markings on the front of the instrument, they say from 7 to 70 megahertz, and yet this oscillator only goes between, well, it goes between 122 and 185, and if we looked at the output on the oscilloscope, we were getting an output between 122 and 185 megahertz. Sorry, whatever, pick a unit and stick to it, I'll try. I couldn't understand what was going on, and I did quite a bit of head scratching, and of course it was just stupid me that I hadn't really looked at the circuit properly, because what this actually is it actually works as a kind of like a superhet. If you actually look at the preceding stage, we've got a mixer here, well, one half of the output valve is a mixer, but going back a bit further, we've got a buffer amp, and then we've got another oscillator here. We've got a 115 megacycles oscillator. What actually happens is we actually get an output of 115 megacycles, and it's roughly 115 megacycles because it's frequency modulated, but it's nominally 115 megacycles. The frequency gets created there. You can see they've got a coil there. Then we've got the second anode here, acts as a buffer amplifier, and then that feeds into the grid of the output valve. And again, the output valve's a double triode. So the first stage there is acting as a mixer. So it's basically what's happening is it's mixing 115 megacycle signals with our variable 122 to 185. And the output should be a heterodyne of that. And of course, well, what I think the problem is, this 115 megacycles oscillator isn't running. So we're actually only seeing, well, I think you call it F1. When you're dealing with mixers, they always talk about frequencies F1 and F2. So we've got an F1 oscillator, an F2, and they're mixing to form an heterodyne, which is the output. Well, for some reason we're only actually getting the output of the F2 frequency. We're not getting the mix frequency between F1 and F2. So that's what my problem is here. I've had a little bit of poking around, and it's not immediately obvious what's going on. It seemed to be that when I wiggled the valve it came back, and it was kind of very easy to believe it was just a bad connection on the valve. But I have cleaned up the valve base and stuff like that. I think more what was happening is when I put my hand over the valve, it was capacitively coupling with something in the envelope and making it work briefly. Or it could just be that something warms up and is dying within the circuit. I'm not exactly sure. Now, it's a little bit hard to demonstrate this, but I'm going to try and switch it on, and what you should see is you're going to see kind of a fundamental frequency which is going to be about 122 megs, and hopefully you're then going to see the heterodyne frequency, which is a wanted signal at 70, and then with a bit of luck that 70 megahertz signal will disappear as this oscillator decides to go tits up. So I'm hoping this is going to work. What seems to normally happen is we see the F2 frequency come up first. That oscillator seems to be a little bit more dominant. Okay, so there's our F2. Okay, here's our 70 megahertz signal. So this is the one that we want. This one here, I think it's that one. It's either that one or that one, I'm not dead sure. Can we put a marker on it in time? But what you're going to find is it's going to die. Yep, that is the one there. Sorry, it's that one there, that little one. You see that's there at the moment. We're generating all these lovely harmonics, all these lovely sum and difference frequencies. But if we actually leave this on, you're going to see as this signal generator, as this pattern generator warms up, that harmonic's going to disappear. I bet it stays perfectly, just to call me a liar now. Oh no, is it going? Is it going? I think it's going. Yep, the Titanic is sinking. Okay, so you can see there that something happened. These are two little signals that we could see before, they've gone away, and I think that's because our F1 frequency, our 115 megacycles, 115 megahertz, God, choose a unit, Chris, that has now packed in, and that's just leaving us with the F2 frequency, which is the main VFO control, because I can vary that, so I can move that around. But we've actually lost the proper output from this pattern generator. As I say, it should be producing a 70 megahertz output at the moment, which is the heterodyne, and it isn't producing that, so there's something not working right. Well, I don't know about you, but sometimes when I'm in the workshop something will happen just to reinforce the fact that I really haven't got a clue what I'm doing most of the time. So what I've just spent the last probably 2 hours doing is just trying to get this frequency control working properly. It was working, and then it wasn't, and then it did work, and then it didn't, and I've been trying all kinds of things, and I think I've had multiple problems. One of the problems was I think some of the valves are probably going slightly low emission, and depending on what sequence you've got the valves plugged in, sometimes it works, sometimes it doesn't. If you mix the valves up again, it stops working. So I think maybe the valves aren't quite right. Certainly we've had some bad dirty contacts on the valve holders, which I've now gone away and cleaned yet again, and also maybe just some intermittent connections around the valve valve holder. So having said all that, I'm kind of feel like I'm back to square one again. So what's just happened now to reinforce the fact that I am an idiot is I've been playing with this variable frequency oscillator, and it's a capacitor type, and what I found was happening is that it seems to have a big dead zone in it, somewhere between 10 megahertz and 40 megahertz. So if you look on the screen now, you can see in the centre we've got our F1 frequency, which is our fixed 115 megahertz oscillator. So that one doesn't change. But you can see to the right of that we've got another signal, and that's our VFO, that's our variable frequency oscillator, that's our F2. Now the problem I've been having is, at the moment I'm now turning the VFO control. I'm swinging it from side to side. And it did move then, but I'm still swinging it. And I'm swinging it by about 50 megahertz, and it isn't moving. I'll go a bit further, up, and then it goes, and it jumps, and then it jumps, goes all the other way. And now, what's it going to do now? Oh, now it's moving again. And now it's moving a lot, and now it's stopped. Now I've actually been moving the dial fairly consistently, and now it's behaving itself again. But what's basically happening is the VFO frequency, it just keeps stopping, and it wouldn't increase and it wouldn't decrease, and I just couldn't figure that out, what was happening. I was looking at all the electronics, I was looking at the inductors, I was looking for a problem with maybe a bad valve or interference from a previous stage. I just couldn't figure it out for ages. So what was causing me all these silly problems was, you can see again I'm rocking the VFO backwards and forwards, and you can see maybe me spinning the knob, but can you see the capacitor here? It's not moving. The plates on this toast rack style capacitor, they're actually not moving, or sometimes it's moving now, and now it's stopped again, now it's moving again, now it's stopped. I think what the problem is, it's simply the grub screw on this controller's come loose, so that as I spin it, it's actually just losing its connection to the knob on the front of the instrument. I'm a fool, aren't I? What a fool. Oh well, these things are sent to testers. So these little grub screws on the side of the variable capacitor, I've just tightened one of them up, and it was completely and utterly undone. It was totally loose. Now I've just gone ahead and I've just tightened up that grub screw, but I've got to admit I'm not dead sure where these plates should be meshed. I mean, when it's actually fully meshed, the VFO control will be at its lowest frequency, and when it's unmeshed, it'll be set at its highest frequency output, the VFO. But then that does get mixed with our 115 megahertz signal, so I'm not sure which way around it's working when it does that mixing. So well, I could think about it. I think it's easy just to give it a try and see if it makes sense, so that's what I'm going to do, I think. Now, in one of the previous videos, people were asking about this that I have connected to my spectrum analyzer. In fact, I've had this connected up like this all throughout this video. So what I've actually got here, I've got a DC blocking capacitor, and then I've got a 75 to 50 ohm impedance converter, and then it goes to the spectrum analyzer. Well, the reason I've got the DC blocking capacitor is that when you're working on valve equipment, it's actually got quite high internal voltages, and if you actually get a fault on this piece of equipment, it wouldn't be impossible for that high voltage to find its way towards the spectrum analyzer. Well, one thing that spectrum analyzers really don't like on them is any type of DC, and in fact just a few volts is enough to destroy them. So you've got to be really careful. I've said in previous videos the best way to connect a spectrum analyzer to a piece of equipment is not to connect it. Find another way of doing it. But if you are going to connect it up, make sure you have something like a DC blocking capacitor installed. And then the other thing we've got here, we've got a 75 to 50 ohm converter. Because the output for this, because this is television and video, this will be a 75 ohm output, so we have a 75 ohm to 50 ohm converter. So let me just adjust our frequency control to 70 megahertz. There you go, pretty much bang on. Well, it may look to some of you that we haven't actually done very much on this video apart from maybe just tightening up a couple of grub screws. Off camera I've actually gone ahead and I've actually measured the resistance of all the resistors, and amazingly enough they're actually within their stated tolerance, which I think is actually pretty amazing considering this piece of equipment is getting on for almost 70 years old now. And I also went ahead and I checked about 80% of the capacitors. Now the reason I didn't check every capacitor is because some of the capacitors are actually shunted with resistors, and unfortunately my LC meter, it doesn't actually take an accurate reading when you've got resistors in series, or maybe have got multiple capacitors in series and parallel, etc. But I have checked 80% of them. Now the other thing that I didn't do, I actually haven't done an actual leakage test on the capacitors, but what I did do is using the voltmeter, I did actually measure the voltage on all the valve grids, and I didn't find any excessive DC. Everything was sat around 0 volts or just below. So again, I was quite happy with that, and again a testament to these capacitors that are 70 years old. And a lot of people said that these mold seals, these Hunt's capacitors, they are notorious for going bad, but yeah, so far so good. They all seem to be behaving themselves for the moment. Now, just for interest, you can see another thing that I've done here. I've just got some pieces of plastic. They were actually lids off something, and I've just cut pieces of square plastic out, and I've just cable tied them onto the back of some of these tag strips, because there's kind of live mains voltages here, and it's not very pleasant if you accidentally touch one, even though I'm running my bench from an isolation transformer. And when you're poking around and putting your hand in, it's often a good idea to cover things up. I mean, I know a lot of people play with things like hi-fi amplifiers and stuff like that, and again they quite often have exposed transformers and tag strips and things inside, and quite often I just get a piece of cardboard and I'll cut it up and just make a shroud, just so when you're taking tests and measurement you don't accidentally put your hand on something, or even like drop the grounded end of a scope probe onto something. So yeah, that's what I did. Unfortunately, I don't have a working 405 line television that we can use to actually test this pattern generator. So in many ways, I think we've done about as much as we can today. But before I say that'll do, there is just a couple of other parts of the circuit I want to have another look at before we finish. So let's go ahead and do that. So I think I'm just going to have a little recap, which is as much for my benefit as it is for yours. So we've spent quite a lot of time today when we're looking at this variable frequency oscillator. And this oscillator produces an output between 125 and 185 megahertz, but the actual output from the signal generator is only 7 to 70 megahertz. So the way this works is it actually mixes this 128 to 185 oscillator, it actually mixes that with a 115 megacycles oscillator, and the output from the signal generator is a heterodyne. So the signal generator has a few settings on it. It has a fixed output, which is just a constant carrier wave, but it also has what you saw earlier as being the modulated video waveforms, and I wanted to have a look at how it generates that kind of modulated carrier output. So you can see down here we've actually got this multi-vibrator circuit, and the job of the multi-vibrator circuit is actually outputs a square wave, and it outputs a square wave at 2 different frequencies. So it can output a frequency of, I think I've got it written down here, of either 400 cycles, or it can output a frequency of 80 kilocycles. So what it will actually do is it's used to modulate our carrier wave into kind of little pulses. So those pulses will either be at a frequency of 80 kilocycles or 400 kilocycles. Now, if we take the 400 kilocycles output first, what that will do is that will produce a series of horizontal bars on the television screen, because I think that's affecting what I would call the frame pulses. It's generating frame pulses, whereas if it's actually set to 80 kilocycles, that's actually going to generate a number of vertical bars on the television screen. So that's why we've got these 2 oscillators here, one of 400 kilocycles and one at 80. But the way it actually works is quite interesting. So the output from this valve here, it produces a square wave, and the square wave is relatively high voltage. And what it actually does is it actually provides a power feed for this VFO here. So what it actually does, it effectively just turns the VFO on and off, and that has the effect of turning on and off the carrier wave output. So what we can do is let's just have a look at this square wave output, and I think we've got to adjust it, because when I was looking at it earlier it certainly wasn't anywhere near 400 and it wasn't anywhere near 80 kilocycles. So I'm just going to adjust that now. So I think what I'll do is I'm just going to connect my scope probe onto this point here, which is actually the output from the multivibrator. So I'm going to connect it at the junction between L4 and this capacitor here, which I think is C14. So let me do that. And of course, for all you test gear aficionados, I'm going to be using the Tektronix TDS 2022B, because I know some of you like to see the old girl. So I think that's the junction point there. What am I set on? Times 10. Quite important to use a times 10 probe, or bigger if you've got it, because two things. One, we don't want to load the oscillator circuit, which I don't think we're going to do, because this is a relatively low frequency. Also, you also want a little bit of attenuation, don't you? Ideally, I guess I'd have a times 100 probe, but I don't have one of them, so we're using a times 10. So I'm just looking at the output from our multivibrator, and as you can see, you can't see anything at the moment. That's because I've actually got the coupling control grounded on the oscilloscope. So I'm actually just going to set my ground reference, and I'm going to set it, where should I set it? I'm actually going to set it more or less right to the bottom, if I can do that. Right, I'm actually going to DC couple this, because I want to have a look at some of the voltages we've got. So you can see in yellow here, this is the waveform from the multivibrator, and I've got the pattern generator set to the line output, which should be 80 kilocycles. Now actually it isn't 80 kilocycles, it's only 41 I can see down there. So we're going to have to do some calibration on this oscillator. But let's take a look at the voltages. So we set the ground reference here at the bottom of the scope. So let me just roughly count up. So we've got 20, 40, 60, 80. So actually the off for our waveform here, for our square wave waveform, it's not at 0 volts, it's actually at 80 volts. And then we've got, that next one is 100, and then 120. So basically the output of our square wave here, it varies between 120 and 80 volts, and this is being fed to actually turn our VFO on and off. So interestingly enough, we're not actually switching off all the drive voltage to the VFO, we're actually just dropping it from 120 volts back down to 80. Let's put a video signal on there and see what that looks like. Now, as you guys already know, I don't know much about video and 405 line televisions. I'm just doing my learning as we go along. But to me, that does look like a pretty crappy video signal. It certainly doesn't look very much like what you see in the books. But what an actual 405 line television would make of that, I'm not exactly sure. As I say, I think that should be displaying a row of vertical bars on the television screen. And I'm guessing these bars would actually be quite wide, because the modulation frequency is at 41, whereas we should be at 80. Now there is an adjustment on the back of here, so I'm going to go ahead and tweak it up now. You can actually see that my whole bench here, it's alive with RF. Quite an interesting thing, just being diverted there. When you actually see there's a lot of shimmer and what looks like kind of noise rippling about on the top of this video waveform. Well, what that's implying is that there's an awful lot of RF energy floating around, a lot of modulation, and some of that modulation is intended, and a lot of it is unintended modulation that takes place. But basically it will make the waveform kind of shimmer, and you may actually find that you can't trigger on it at all. As it happens, I'm actually triggering on the multivibrator output above, so that's okay. But when you have trouble triggering on waveforms, that's generally because they're complex, and I say they may be rich in harmonics. What I was trying to say is, I think it's very interesting that the output from this signal generator, it should actually be between 7 and 70 megahertz, yet we could actually see on the spectrum analyzer that actually the things like the VFO output, the 125 to 185 megahertz, that signal was actually higher than the heterodyne which the pattern generator is supposed to be putting out. And the same for the 115 megahertz signal, which is used in one of the mixing stages. So although this thing is actually designed to output a 70 megahertz, it's actually also outputting one at 125 and one at 115 as well, and we're actually seeing the effect of all that here. So my whole bench is alive with RF at the moment. It probably doesn't help that this thing isn't nailed down in its case, of course. It needs screening around it. Okay, I'm waffling again, aren't I? Let me just adjust this. I'm sure one of these will do it. It's not that one. Oh, it looks like it's that one. So all I'm going to do is I'm going to adjust this now, this control here, until this reads down here 80 kilocycles. 44, 46, 48, 50, 55, 60, 72, we're getting there now, coming up to it, 72, 78, 81, gone past it, go back a bit. Making tiny adjustments. Okay, we're at 80.1. Can we do any better? That's actually not bad, I don't think. Okay, 80.057. Close enough, I'm sure that'll be fine. So that's the 80 kilohertz multi-vibrator output, which is used to produce the vertical bars on the television screen. That's now calibrated, that's good enough. So now we've got to do the lower frequency oscillator, which is 400 kilocycles. So let me go ahead and switch it to the 400 range. And obviously 400 is a much lower frequency, so we need to adjust our time base. So we've got our 400 kilocycle one switched in. At the moment it's at 280, so let's just increase the frequency a bit. That's 307, 340, 390, 397, so we're just a midge's dick off now. 401, can we get it bang on 400, can we score? Okay, 400.7, I'm going to call that quite good enough.